Hi, everyone. Welcome to Fractional Excitations, the podcast from Tufty Lab at Boston College. The purpose of Fractional Excitations is to discuss the human aspects of research in quantum materials. Every time our group has a new publication, we have a conversation with a graduate student who was the lead author of that scientific article, and we discuss the challenges they faced and the triumphs they had in the course of performing the research. Today, we're going to discuss with the fourth year PhD student Xiaohan Yao, who published a scientific article in Physical Review X about spiral ordering induced by Weyl electrons. Xiaohan has performed detailed experiments to elucidate a new piece of physics in which, while fermions, that are relativistic quasiparticles in condensed matter physics, are responsible for magnetism. The role of Weyl fermions in magnetism has not been properly understood until now, and my student Xiaohan started an experimental project to understand the magnetic properties of these Weyl fermions that are relativistic quasiparticles at low energies. Hi Xiaohan, how are you?
Hi, Father. I'm good. Thank you. How are you?
Good, excellent. I will start with the first question, Xiaohan. Could you explain to our audience how did you begin this project? Tell us about the motivation and the goals of your project.
Sure. Thanks for the introduction. When I was a new PhD student in Tufty Lab, one of our senior students, Weyl Yang, he helped me a lot. At that time, he did some work on cerium aluminum silicide, and the group find that this compound family, rare earth aluminum silicide, is magnetic Weyl Semimetal with like normal properties, and that would be an interesting start. So at first, I just want to follow some of his work, but when the idea is that one of our collaborators, project, did some theoretical work, and he predict that the Weyl electron could participate in magnetic interactions. We know that most of people they study Weyl Semimetal because they are interested in the non-trivial topological properties, but they are not really interested in magnetism. But we find out that Weyl electron could participate in magnetic interactions and give rise to topological magnetic defects such as Skyrmion or spiral order. So our motivation for this work is to find the experimental evidence of such a true spiral order and prove that this Weyl-mediated RKKY interaction could open up a new mechanism for topological magnetic defect. We first studied neodymium aluminum silicide and find that Weyl electron did participate in the interaction and coupled with the localized spin. But neodymium aluminum silicide is not a true spiral order. It is instead a ferrimagnetic order up-down-down with a very small canting. Therefore, we continue our study in this family compound, rare earth aluminum silicide, and I focus on samarium. We hope that we could build a true spiral order.
Excellent. Thank you for explaining the goals of the project. As you correctly mentioned, this was a search for spiral magnetic ordering in materials mediated by chiral Weyl fermions. These are quasiparticles that are chiral in nature, and the question that Shahan was trying to answer was whether the chirality of these new particles can induce a spiral texture in the magnetic ordering of the material, and she answered that question positively, in fact. With that, we will go to the next question, which will come from another student in the lab, Sudaman Balguri.
Hi everyone, this is Sudaman. Hi Shahan, I just want to ask, can you briefly interpret the main results of your work? What makes the discovery more interesting or more important?
As I said in the motivation, we realized a truly spiral order with a fairly new mechanism. As Fazil said, the Carroll-Weyl fermion participated in magnetic interactions, and this is the first truly spiral order realized with this well-mediated RKK interaction. And also, we provide multiple experimental and theoretical evidence for our work to make it more convincing and compelling. The key insight in this work is to recognize that which is necessary to establish a spiral order. We also combine this work with our previous research, the neodymium study, and have a better understanding of this new mechanism. What makes this discovery important is that there are several implications of our discovery. For example, like well-induced RKKY interaction, as I said, is a new mechanism for stabilizing spiral order and skyrmion, and that are in demand for high density and high speed magnetic memories. So that could be one of the applications of our work. And in physically, as I said, that's a fairly new mechanism, and we explain some necessary conditions for this new mechanism, such as magnetic crystalline anisotropy, and we also provide a lot of experimental and theoretical study on this.
With us here in the recording studio is also Enrique Gonzalez, who's going to ask the next question.
Hello, everyone. Hi, Xiaohan. It's Enrique. My question for you is, who did you work with most closely during this process? And if you can talk a little bit about them, where are they from? And how did they contribute to the work you've done?
Hi, Erica. One of my collaborators who did the very important part for our work is Jonathan Gordate from NIST, National Institute of Standards and Technology. And he is also the second author of our work. He did the whole neutron scattering part, the neutron experiment, and did a lot of work on, for example, analyze the neutron data and combine that with symmetry analysis to find 6 possibilities of the magnetic order in our system. He helped me a lot with when I'm writing the draft. He gives us very good suggestions on our data analysis. That's one of our collaborators. And another collaborator is David Graff from MagLab. Because this is a magnetic Weyl Semimetal, so we go to MagLab, which has the highest magnetic field in the world, and we measure the magnetic torque there to have a better understanding of the magnetic behavior of our Semimetal SmAlSi. Also, the data from him contribute a lot in our phase diagram.
Excellent. Thanks, Enrique, for asking the question and Xiaohan for answering the question. The next part of this conversation is about some of the challenges that you were facing during the course of the project, Xiaohan. Now, maybe I should give our audience a bit of introduction about this challenging project. Xiaohan made crystals of samarium aluminum silicon with extremely high quality. She performed quantum oscillation experiment at extremely high magnetic fields in the National High Magnetic Lab in Tallahassee, Florida, and she performed theoretical calculations to understand the detailed theoretical properties of these Weyl fermions and spiral magnetism, and she collaborated with Jonathan Gaudet, as she explained, from National Institute of Standard and Technology to understand the magnetic properties of these materials. So it has been a highly collaborative and multifaceted project. And at the center of all of those efforts was this one student, was Xiaohan, with whom we're talking today. So Xiaohan, maybe tell us first, tell our audience, how was this experience for you to lead a collaborative project, to work with multiple scientists, and to go to these national labs to perform your experiments?
Mm. I think it's a really great experience to work with multiple peoples in different labs. Like For example, one of our collaborators, Jonathan Gordon, he is an expert in neutron scattering. With this collaboration, I learned a lot from him and learned a lot about the neutron scattering, what neutron scattering could do and how powerful it is. And also, it's a great experience to go to MATLAB by myself and do some experiment there, make some device and do the measurements guided by David Graff in MATLAB. And David Graff is also a very good person to work with. Like when you work with multiple people, each of them are expert in one aspect, and you could learn a lot from them. One cannot be expert in all of these aspects, all of these measurements, but if you learn, collaborate with more experts, and you could learn a lot, and you could make your study, make your research more complete. You could write a whole story in your paper.
Excellent. You published your paper in Physical Review X, which is one of the more difficult journals to publish in because the standards are very high in this journal. I know that you face some challenges in the peer review process. Could you tell our audience what were those challenges, how difficult it was sometimes to provide answer to those challenges, and how you handled it in the end?
The first challenge, I would say, before we submit our paper to the review, samarium is not a good material because it has a very large cross-section area for neutron scattering. So it absorbs a lot of neutron beam, but it won't give us a good data for neutron scattering. But for neutron scattering data, we need a high resolution to do the following symmetry analysis to find the magnetic space group, to find the magnetic order of the system. But samarium is not a good material for neutron scattering because it absorbs a lot of signals. And with the help of our collaborator Jonathan, he helped a lot in upgrade the whole neutron beam and increase the intensity of the beam for 3.5 times of the previous one. By doing that, we increase the intensity of our signal. But still, because samarium absorb a lot, so even though we make a huge progress in the neutron scattering, we still cannot get good data with a very high resolution. That also gives us some challenge when we face the referee. Because the referees think that the neutron scattering data is good, but you cannot perform a better symmetry analysis based on that. So the referees want us to provide more direct evidence of the spiral order, like some really time-consuming experiments, and that we cannot make it with a short period of time. And we try to improve our results. We try to improve our data and find more experimental and theoretical evidence. But all these evidence, like for example, transport, quantum oscillations, heat capacity, and some DFT calculations, Monte Carlo simulation, these are all indirect evidence. So we argued for like 3 times to the referee, and finally a third referee joined, and he thought our work is really compelling and convincing. Then we finally make it.
That's right. The From submission to publication, this work took about a year. It was a year of battling with referee. Every time they would ask very difficult questions, and they would propose sometimes experiments that could not be performed because, as Xiaohan explained, isotope rich samples of samarium, aluminum, silicon could not be made because isotope rich metallic samarium does not exist. During this process, when you would get referee reports that were like this, that were somewhat negative and difficult to answer, how did you feel about such reports? And how did you pull yourself together to go back and fight again and try to get your work published. It was a year of this battle, so I'm imagining it should not have been an easy experience for you. Could you elaborate on that?
Like we received a report from two referees, and but each of them gives us both positive and negative like points, and I'm quite impressed by the positive points said by the referee. Like for example, some of the referees said he or she find our work fascinating and almost convincing. He or she said our data are of high quality, and the referee find that and they admit that. That impressed me a lot, and after that I will look into the negative points like they said. And for example, if he say something that we cannot really make it. Like he wants us to find direct evidence, but that is really time consuming, and we cannot make it. We don't have that equipment. We are just trying to prove more other evidence to make our story more fascinating, to complete our works in some other aspect. Like we provide a lot of indirect evidence, but I'm trying to think that we are almost done. Like they think they at least they admit that we have a lot of positive points in my paper.
Okay, the next question comes from Sudaman.
Shahan, I want to ask you, what are some important lessons in general about research you learned from your stay in Tafti Lab and doing research in Tafti Lab? And also, could you give some advice for your junior students like me, or in general, any future students?
Thank you, Sudan. The most important lesson for me when after I joined Tafti Lab is the importance of collaboration. Because when I was an undergraduate, I also joined a lab, but because labs and labs are quite different with each other. And Tafti Lab is different in a way that Professor Tafti know a lot of people. They are all expert in different measurements, in different aspects. And in our own lab, we only have, for example, transport, crystal growth, and heat capacity, and we only have limited approach to our study. But Fazil knows a lot of people, so we could just talk to each other, share our ideas, and try to convince them that our study is interesting and let them collaborate in this work. That's the most interesting thing, because with the help of the collaborators, we are not limited to our the physical equipment in our lab, and we could also learn how different people do works, how different people think about a research about a project. I learned a lot from different people in different labs. And also, when, for example, in the big conference like March meeting, we could always talk to our collaborator in person, and that's a very good experience for me. Otherwise, I think go to conference and know more people, learn from different peoples. Don't only work by yourself. For example, I learned some knowledge in neutral study from Jonathan, and in theoretical works, I collaborate with a theoretical group, and I know DFT calculations by myself, but I learned from the theoretical group, and they are doing different ways in DFT calculations, and we compare how we did things differently, and I learned a lot from them. Thank you.
Thank you, Xiaohan. The next question is coming from Enrique.
How does it feel for you to give a talk at the APS meeting? And can you talk about how that experience went?
For your first question about the experience giving a talk on APS meeting, to be honest, when I prepare for it, I prepare 1 month in advance because I was really nervous for that. This is something fairly new. It's a new mechanism, and I was afraid that some audience give me a hard time, give me some tough questions. So I prepare like 1 month in advance and try to make good cartoons, try to make good animations, let them understand it in a better way. But when I was giving a talk, I think I'm just focusing on what I want to say. I'm not nervous at all when I was talking there. And a lot of audience came to my talk, and that's a good thing because I think they are really interested in my work. And also because it's a 10-minute talk and with 2 minutes for questions, and there are a lot of people that try to ask me a lot of tough questions, but I tried my best, like with the best of my knowledge to answer them. And also after the talk, there are many people contact me, try to have more collaborations on this project, or we talk in person. So I think it's a very good experience.
Thank you, Shahan, for answering to Enrique's question. Our last question is about your future plans for the continuation of your research related to Weyl fermions and Weyl semimetals. Maybe you tell us briefly about what future plans you have for such a research direction, and also tell us about your future goals in general as a graduate student for the continuation of your PhD.
Thanks, Fazil. I think for in research, my future goal is because we know that magnetic Weyl semimetal is quite interesting, and with the chiral Weyl electron participate in the system, it become more and more interesting. And one important element in this group of material is the screw axis. So I'm interested in such symmetry, non-central symmetry space group with a screw axis, and with these symmetry elements, most system will have a Weyl electron participate in the system. So I'm interested in some similar system, like with Weyl electron. It could participate in magnon, or it could participate in phonon, something like that. So my future goal as a graduate student is that I want to collaborate with more different groups, learn more experimental details, learn more how to do some experiments in different aspects, different approach, and also learn something in theoretical works to have a better understanding of different mechanism. Thank you.
Excellent. Thank you, Shahan, for sharing with our audience the story of your research on spiral magnetism in Weyl semimetals. A quick word from me about Xiaohan is that I believe Xiaohan is a technically very strong student. She's done truly exceptional work in this project. It hasn't been easy to lead a research that includes three national labs, approximately, let's say, 10 plus co authors, and both experimental and theoretical research. This is something that Xiaohan has been at the center of it. She has led the project, and in almost every aspect of it, she's done an excellent job. As an advisor, it's really a pleasure for me or for any other advisor to see their students taking the lead in a project and being able to handle difficult and challenging situations. And Shahan did very well throughout this project. So, congratulations to you, Shahan.
Thank you.
I would like to also thank Enrique, Sudaman, and Elena who have been helping with the recording of this episode. Thanks, everybody. All the best.